Namaskar. For today's lecture in the paper of Microwave Electronics for the MSc classes, we will discuss the parametric amplifiers or the Varactor Diode. The parametric amplifier word signifies that the operation of the amplifier depends upon the variation of one or more parameters with time. It is a low noise amplifier capable of amplifying microwave frequencies. The basis of the parametric amplifier is a voltage variable reactance which is of capacitive nature, and the Varactor diodes, especially the linearly graded junction diode and the abrupt junction diodes, are used for the amplification of the microwave signals. Now we understand first the basic principle of the operation of Varactor diodes, that how the time varying capacitance can be produced or initiated in our microwave circuits. So we consider a parallel LC circuit as shown in the figure, and we will plot the capacitor voltage against the time. If we assume a physical mechanism by which we can vary the spacing between the capacitor plates. Now if the capacitor plates are pulled apart, when the voltage across the plates is maximum as is shown at the point X, then as we increase the spacing between the plates, the capacitance will decrease, and by the relation V equal to Q upon C, the voltage across the plates is increased. So this has been shown in the diagram by this change in the peak of the capacitor voltage. Now, and the charge across the capacitor plates must remain constant, what it was when the voltage reaches its peak value. Now the work is done when the plates are pulled apart to separate the charge. The total energy in the system has been increased by the source which separates the plates. The energy transfer is referred to as the pumping, and the source supplying this energy is called a pump. So this is important part here which will be used in the principle of the Varactor diode. Now further, when the capacitor plates comes to its normal size by the physical mechanism, and the capacitor starts discharge, the energy stored inside the plates in the form of the electric field is now converted into the magnetic field energy surrounding the inductor. Now when the plates come to its original separation at the point Y in the figure, when the voltage is 0, then there will be no charge on the plates and no work is done, and the voltage remains unchanged. This is shown at this point Y. Now when the voltage goes to a minimum between the capacitor plates, now again at this point Z, again the capacitor plates were pulled up by the physical mechanism, then the work will be again done on the capacitor by the pumping voltage. The energy will be supplied by the pumping system, and again additional energy will be supplied to the system at the point Z. So this device, which is used to obtain variable capacitor at microwave frequency, it is called Varactor Diode. The Varactor is a low noise diode which has a highly non-linear CV relationship as shown in this figure, and in the adjoining figure this is the equivalent circuit diagram of the Varactor diode. The frequency at which the quality factor, which is given by 1 upon omega CR when it is unity, that frequency is referred as the cutoff frequency. Now we will discuss the practical application of this varying capacitor. First of all, we discuss the linearly graded junction diode. The construction of the linearly graded junction diode and its operation is shown by these figures. So in this first figure, the difference between the acceptor and the donor atom densities is plotted against the distance across the depletion layer, which is assumed at x equal to 0. So in the region between x equal to plus d by 2 to 0, the density of the doping donor atoms will be decreases and from d by 2 to 0, and then gradually increasing the number density of the acceptor donor atoms in the p-type region between x equal to 0 to x equal to minus d by 2. So in the depletion layer, this variation of the number density difference in a minus nd will be linear. In the second figure, in the second diagram, we have shown the space charge density across the depletion layer. So in the depletion layer is not completely free of charge carriers. So there are positive and negatively charges respectively in the n-type and the p-type regions around the depletion layer. And this is the diagram when a reverse bias voltage is applied across the PN junction diode. Now the Na minus Nd, since it is linear, that is proportional to x, so this is given by equation 1 where k is a suitable constant. Similarly, the space charge density rho is also proportional to x, or we have assumed rho equal to qx. Q is also a constant. Now the one dimensional Poisson's equation is given by d2 phi over dx square equal to minus rho over epsilon, since rho equal to qx. So this is shown by equation number 3 where phi is the potential. Now integration of this equation third with respect to x will give us d phi over dx equal to minus q x square upon 2 epsilon plus a constant of integration. The electric field across the junction is given by equal to minus d phi over dx. So the electric field will be 0 beyond the depletion layer, that is when x is greater than or equal to d by 2, then the electric field will be 0. So applying this condition to equation number 4 will gives us the value of the integration constant A equal to q d square upon 8 epsilon. On substitution of value of A in equation number 4, then further gives us d phi over dx equal to minus q upon 2 epsilon into x square minus d square by 4. Again integration of equation number 5 with respect to x will gives us the expression for phi with integration constant again b. Now to find out the value of b, again we consider that at x equal to 0 the potential phi is 0. So this condition will gives us the value of V equal to 0 with equation number 6. So therefore now we will have the expression for the potential phi given by phi equal to minus q x upon 2 epsilon into x square upon 3 minus d square by 4. The potential difference across the junction will be the difference of phi n and phi p, that is phi n minus phi p will be given by phi into d by 2 minus phi at minus d by 2. So substituting in equation number 7 the values of x equal to plus minus d by 2, this will gives us phi n minus phi p equal to q d cube over 12 epsilon. So now in the equilibrium condition, this must be equal to the contact potential phi c across the junction plus the negative bias applied potential, that is minus v. So therefore phi c minus v will be given by q d cube upon 12 epsilon. Now we find out the total charge stored across the junction in per unit square area. So this can be computed by q equal to integration between 0 to t by 2, that is on the other side of the junction, and of rho dx. Rho is equal to qx. So this will gives us after integration q d square by 8. Now eliminating the value of d between equation 8 and 9, this will gives us the value of q given by equation number 10. Also now if we calculate the capacitance C, which is the ratio of q and that is the decrement in charge to the decrement in the potential across the junction, that is dq over d phi c minus v. So from equation number 10 after differentiation, this will gives us the value of the capacitance for the linearly graded junction diode. Now it is also interesting, if we put the value of phi c minus v from equation number 8, then this expression for the capacitance will comes out to be C equal to epsilon upon d. So this is the similar relation for a parallel plate capacitor with unit plate areas, because the capacitance for a area A and separation D is given by C equal to epsilon into A upon D, since here we are considering the area of the plates as unit area. So therefore this expression is similar to the capacitance of a parallel plate capacitor. Now if we consider phi c minus v equal to v0, and in addition a pumping voltage Vp equal to Vp cos omega pt is also applied, then the expression for the capacitance C from equation number 11, this will be changes to, because here we will change the value of phi c minus v by v0 plus vp. So after simplification, this will comes out to be C in the form of Ct given by equation number 13, and this shows that the junction capacitance is a non-linear function of time and it varies with time. So this is the variable capacitance. Similarly, we can also find out the expression for the capacitance for the abrupt junction diode or the diffuse junction diode. So in the abrupt junction diode, the space charge density suddenly or abruptly changes across the junction as shown in the figure, and the entire almost entire depletion layer lies in the n-type region, that is the width in the p-type region of the depletion layer is very small, and the almost entire depletion layer lies in n-type region. Also Na will be very greater than Nd, since we know that the total charge will remain 0. So that is, in both the sides the charges are given by Q Na into Wp in the p-type region plus Q into Nd into Wn in the n-type region. This will be 0. Cancelling Q, this will give us Na into Wp equal to minus Nd into Wn. Since Wn is very large as compared to Wp, so therefore Na will be very greater than Nd. So this is shown by this reason that this is the value of Na and this is the value of Nd, which is very small as compared to Na. So this can be understood by this space charge density, and the graphs for the potential and the electric field across the junction are also shown in the figure. Again, now taking into account the one-dimensional Poisson equation, that is d2 phi over dx square equal to minus rho over epsilon, since here rho is equal to Q into Nd. So now integration with respect to x will gives us d phi over dx equal to minus Q Nd upon epsilon into x plus constant of integration a. Now the electric field will be 0 for x greater than or equal to Wn, that is at the boundary of the depletion layer, which is almost equal to d, although d is equal to Wn minus Wp, but Wp is very small, so we can assume here Wn equal to d. So therefore the electric field, which is given by negative gradient of the potential, that is minus d phi over dx, that is minus Q over epsilon into Nd plus d plus a. So here we have substituted the value of x equal to d here. So this will gives us the constant a equal to Q Nd into small d over epsilon. Substituting this value, this will gives us the d phi over dx given by equation number 15. Now again integration with respect to x. This will gives us the expression for the potential phi with constant of integration b. To compute the value of v, again we put the value of x equal to 0, at which the potential phi is given by 0. So this will gives us the value of b equal to 0. So finally this will gives us the value of phi equal to Q Nd into x upon epsilon into d minus x by 2. The potential difference across the junction, which is given by phi n minus phi p, that is phi at x equal to Wn minus phi at x equal to Wp, which is nearly equal to phi at Wn. So this will gives us the value which is given by equation number 17. Now again in the previous discussion, as we have computed the value of Q for the linearly graded junction diode, again Q is given by integration between 0 to d rho dx. Substituting for rho, this will gives us Q into Nd into d, and eliminating the value of d, the expression for Q will be obtained as shown in the equation. Again, C is given by dq over d phi c minus v. So after differentiation, this will gives us C equal to Q N d epsilon upon twice phi c minus v power minus 1 by 2. And again, if we eliminate phi c minus v, this will again gives us C equal to epsilon upon d for unit area. It means again this expression is similar to the expression for the parallel plate capacitor. And again, if we assume phi c minus v equal to V0, and in addition a pumping voltage Vp is applied across the junction diode as it is shown in the figure, in which a time varying pumping voltage signal Vp equal to Vp cos omega pt is connected. In addition to the V0, the expression for the capacitance will become Ct equal to Q N d epsilon upon 2 V0 power 1 by 2 and into 1 plus Vp over V0 cos omega pt power minus 1 by 2. Again, this shows that the junction capacitance is time varying and it varies non-linearly. Only the difference between the capacitance of the abrupt junction diode and the linearly graded junction diode is only this power, that is power 1 minus 1 by 2 in the case of abrupt junction diode, and here in the case of linearly graded junction diode the power is minus 1 by 3. So in both the cases the capacitance varies non-linearly with the time. So therefore both these two diodes, that is the linearly graded junction diode and the abrupt junction diodes, will be used as the time varying non-linear capacitance, that is the for the Varactor diodes, and these will be used for the amplification of the microwave signals. So this is the again the non-linear circuit, equivalent circuit of the Varactor diode, when this diode is encapsulated inside this cartridge material. This is the outer cartridge material. So when it is encapsulated, then additional shunt capacitance Cp due to the cartridge material and the resistance of the cartridge material Rp, these were also come in addition to the Ct in the equivalent circuit, and also when the leads were also present and put on, then the capacitance Ls, inductance Ls, that is the series inductance, will also come into account. So this is the equivalent circuit which will be used in our further analysis of the parametric amplifiers. The order of C and Cp is of few picofarad. Series inductance Ls is of the order of 1 nanohenry, and the cartridge resistance Rp is of few ohms. So this is the equivalent circuit. In our next lecture we will discuss the Manley-Rowe relations, which were the power conservation relations, and with the help of the Manley-Rowe relations we can judge the efficiency and the performance of any parametric amplifier. Thank you.